Hello, and thanks for using TickBoom. In this video, I'm going to work through part 3 of this 4-part question, question 8b, which is the final question of the 1989 New South Wales HSC 4-unit exam. So if you haven't watched my videos on part 1 and part 2, I recommend that you do. This is one of those questions where each part builds upon those that came before it. So to be able to kind of think sensibly about this part 3, you really need to have worked through part 1 and 2. So if you haven't already, go do that. Otherwise, if you have, stick with me as I work through part 3. Part 3 says to suppose that b is an irrational number. Let capital N be a positive integer and consider the fractional parts of fb, f2b, and so on, all the way up to fn plus 1b. Part alpha of this part then says to show that these n plus 1 numbers, fb up to fn plus 1b, are all distinct. And then part beta says to divide the interval x greater than or equal to 0 and less than 1 into n sub-intervals each of length 1 on n, and show that there must be integers m and n with m not equal to n, and m and n each between 1 and n plus 1, such that the fractional part of n minus nb is less than 1 on n. And I think here with this part 3 we're starting to see things get a little bit more interesting. I think we're starting to see why this question got its reputation as the hardest ever question on a mathematics exam in the HSC. So I think part 1 and 2, as you would have seen in my prior videos, are fairly doable. You know, maybe not easy, but definitely not hard in and of themselves, not kind of worthy of that reputation as being the hardest ever. But I guess part of the critique of this question was that it was very long, and for sure, you know, even just this part 1, 2, and 3 alone would make this quite a long question. That there's even a part 4 to come next means this really was quite long, and I think these last two parts, part 3 and part 4, are going to make things more interesting, and definitely probably difficult enough to see why this question got the reputation that it did. So picking up from where I just left off with part 2, I'll just turn over. So we're now in part 3, where we're told to consider the fractional part of b, the fractional part of 2b, and so on, all the way up to the fractional part of this n plus 1b, where n is an integer, and we're told that b is irrational. So we've got n is an integer, and b is irrational. So that's the kind of background to this part 3. And like the other parts before it, it got broken up into 2 subparts. So we had part alpha, which says to show that these n plus 1 numbers are all distinct. And at this point, yeah, I guess you got to think, well, what are the options available to me? I think proof by contradiction is the most straightforward way to go about proving something like this, because all we have to do is assume the opposite and show that that leads to a contradiction. So let's use contradiction here. And in doing that, let's assume that the n plus 1 numbers are not all distinct. So what that means is that some of them may be distinct, but there's at least 2 that aren't distinct, 2 or more that are not distinct. So what way we could write that is that therefore there are at least 2 integers, and let's call them m and n such that the fractional part of mb is equal to the fractional part of nb, i.e. they're equal, so they're not distinct. Now, and I should probably say that this is where m is not equal to n, and also m and n both have to be between 1, and so m and n have to be between 1 and n plus 1. Alright, so now at this point we can see almost the purpose of why the question writers got us to do part 2, because remembering from part 2 we were asked to show a few things, and particularly in part B we were asked to show that if the fractional part of two numbers, mr and nr, if they're equal, then r must be rational. So we can point that out. So from 2 beta, we know that f of mr is equal, if f of mr is equal to f of nr, then r is rational. Therefore, if f of mb is equal to f of nb, then b is rational, because all I've done there is replaced r with b. So you can make the same conclusion. But that's our contradiction right there, because we're told in the question that b is irrational. So what we see is that when we make this assumption that the numbers are not all distinct, we get to the conclusion that b is rational, but that can't be true because our starting point, what we're told, is that b is irrational. So therefore, it must be the case that the n plus 1 numbers are all distinct. And that's what we were asked to prove. So I think proof by contradiction gets us there for this part alpha. Now moving on to part beta, we're asked to show that the fractional part of m minus nb would be less than 1 on n, where m and n are integers, and m is not equal to n, the lowercase n, and as I kind of noted before, m and n would be between 1 and the capital N plus 1. So that's what we're being asked to show. Now, from alpha, from the part we just worked through, we know that all of these numbers are distinct. They're all distinct. We also know that all of these numbers are fractions. They're all between 0 and 1. That's the definition of a fraction. So therefore, we can apply the pigeonhole principle here. So we can say if we divide this range 0, say x between 0 and 1, into n sub-intervals of equal length, one on n, which is what the question told us to do, then by the pigeonhole principle, at least 2 of the numbers will fall in the same sub-interval. So I'll just take a moment to explain that. So we've got this range x between 0 and 1. We've divided it into n subintervals. So there's n subintervals to place a whole bunch of numbers. They've each got a length of 1 on n. But we've got n plus 1 numbers to squeeze into these n subintervals. So by the pigeonhole principle, if you kind of visualize a whole bunch of pigeonholes, and each of these numbers has to fit into a pigeonhole, well, they're all distinct numbers. So, you can put FB into one pigeonhole, F2B into another, and so on. But eventually, because you've got n plus 1 numbers to place, you're eventually going to run out of pigeonholes. And there's going to be at least one of these numbers that has to go into a pigeonhole that's already full. So that's what we mean when we say at least 2 of the numbers are going to fall in the same subinterval. So therefore, there must be 2 integers m and n such that fmb minus fnb must be less than 1 on n, since they're both falling into this subinterval of length 1 on n, so the difference between them must be less than the size of that subinterval. For our 2 requirements, m not equal to n and m and n between 1 and capital N plus 1. So that's kind of what we're dealing with, but we need to now get this fmb minus fnb into this format, and then we would have done the proof. So I'll just have to turn over at this point. Let's start with fmb minus fnb. Now the first thing we can say is that that's going to be equal to the fractional part of itself. So fmb minus fnb. And we can say that because the fractional part, by definition, is between 0 and 1. So if I take the fractional part of 2 things that are already fractions, then it will remain unchanged. Taking the fractional part hasn't done anything to those numbers. So we can do this. Now the reason that's going to be helpful is now what I'm going to do is write each of these in terms of that result that I pointed out earlier, where you can write a number as its integer part plus its fractional part. So the fractional part is the actual number minus its integer part. So that means fmb will be mb minus the integer part of mb minus fnb, which would be nb minus the integer part of nb. So that's going to be the fractional part of, and now let's just expand this. So we'll get mb minus nb, and we'll get minus I can put this in brackets, minus I of mb minus I of nb. Because that'll be minus I of mb minus minus gets you the minus minus, which is the plus. So that is a correct thing. Now, this we can then say, kind of doing the reverse of what we did here, the fractional part of each of these things will be the fractional part of mb minus nb minus the fractional part of I mb minus I nb. So now that we've kind of got the fractional part of this minus the fractional part of this, hopefully you can see this will simply be 0, because the fractional part of the difference between 2 integers, well, there will be no fractional part. So this just becomes the fractional part of mb minus nb, but I can then kind of factorize and say m minus nb, and that actually is what we were working towards. So if fmb minus fnb is less than 1 on n. And fnb minus fnb can be written as this. We can therefore conclude that fm minus nb is less than 1 on n as required. And that there is part 3 done. And admittedly, this definitely was a bit harder. I can see how a lot of students probably wouldn't have got these 2 parts. I could imagine plenty would have probably got to contradiction eventually and made the linkage between this and the prior part where we had made this result. Part beta, yeah, maybe not everyone would have thought to go to the pigeonhole principle. I think the question writers were definitely trying to guide us there by telling us to divide into these n subintervals. Whenever you see I've got n plus 1 items into n subintervals, hopefully pigeonhole principle kind of jumps out at you as being relevant, but maybe it wouldn't have jumped out to everyone. But nonetheless, that is how you tackle part 3, so hopefully that's all made sense. Now I'm going to move on to the final part, part 4. And as I mentioned in my earlier videos, whilst I have a way of thinking about part 4, I actually don't know if my approach is completely right. And it's partly because I think it's almost too easy. And therefore, if it is really that easy, how could this question have its reputation as such a difficult question? So it's almost like a catch-22. I've been told this is the hardest question in history, or at least the history of 4-unit math exams. I've kind of worked through it, and so far it hasn't been that difficult. So surely part 4 must be the clincher. And so given my little hesitation in my approach, I'm assuming I must have missed something, but I'm not sure. But anyway, keep your eye out for the next video, part 4, and you can see for yourself whether I must have missed something or not. Yeah, tick boom.